overview of the interdependent network of the cooperation, and also to show you how we can achieve the consensus with evolution gain. Besides, I will also show you how can we achieve the distributed optimization with evolution gain. So, the talk here many involve my students and also others from Wu Bin and Wang Zhen who is here. And I can see this time because everybody here in this room believe that cooperation is ubiquitous in nature and also in our human society activity. But also we also have known that from the biology and economics, many reasons show you that generally we cannot achieve cooperation. So some times ago that in our work have shown you some rules have summarized to achieve cooperation, for example from the king selection and others. And many here we can show that many focus on the network reciprocity of the cooperation. And for example, on the network, so there is some work to give the condition to achieve cooperation. For example, the B over C is larger than K. The K here is the average degree of networks, and the many on the regular structure of the graph, right? Another one could be the some strange thing. Okay, another one could be a kind of the finite homogeneous graph. There is a similar conditions like that, but here is the size of the population. This one maybe some change of the slides. Anyway, main attention on the cooperation and mainly focus on the isolating a single network. For example, every network or every population here could be mapped to a static and single structure. However, we can have many examples here. We know that the complex large-scale networks and systems have shown very strong interdependent structure. So, for example, the power grid and computer network. There is a various chaos. Some interdependence between two networks. Others could be a community network and L1 global web. So on this interdependent structure, if we assume the static structure, there is some results on the cooperation. For example, the Wang Zhen here and the Zhang Lolo we heard show you that some results on the stronger the bias and also the intermediate interdependence to facilitate cooperation. So we step further to a dynamic structure. So that means there is not only the structure evolution, but also the structure evolution should co-evolving together. We can show you that if there is some with the probability omega, that's the many study the structure evolution. Another one with 1 minus omega probably, that's a structure evolution. Here, if there is an evolution structure, there is some 1 minus alpha to switch to another connection between two different populations. Otherwise, there is still a new link inside the same population. So we here only focus on the prisoner's dilemma, the standard gain model, and we show you with the family rule, and also there's a payoff matrix. Those results is a little bit here. As a selection could be favor the cooperation when such conditions stands. Here we can show you that we should focus here. That there is a very bias of alpha, show you the intergroup bias. So that means the alpha here dominates the change of the structure between the groups or between populations or just inside the population. So the alpha here favor the cooperation, but if the alpha is too big, may also inhibit the cooperation. So just means the moderate intergroup bias could maximize the cooperation for independent population. So here we only as the first story of the cooperation, and I think there are too many fruitful and important results as we can show the schedule of this workshop. So we mainly focus on the more than cooperation. The first is that we consider the behavior consensus. For example, from the biological and social, motor, opinion formation like that. So there is many examples of the behavior consensus. However, the main intention of the consensus still remain on the single and isolated structure. So there is now very strong result on the interdependent structure. Besides, it is not clear such interdependent structure affects stabilization of consensus. Besides, we still wondering whether or not the evolution role to achieve such a cooperation and consensus. So when we think the evolution is the driving force of the system, how or where such consensus could be observed. Anyway, we mainly focus on a mutual, like there is non-selection. Otherwise, the weak selection and the strong selection like that. But the question is, how does such selection affect the emergency and the stabilization of consensus on dynamic interdependent structure? So we still, with this dynamic structure, the probability omega to change the strategy and the 1 minus omega to evolving the structure, and also 1 minus alpha inside between two groups, and alpha to change the connectivity inside the same group. Here, we not focus on the prisoner's dilemmas game, just as a kind of a very general payoff matrix. So here you can see that we do not pay as much the C cooperation or deflection like that. We just focus on two general strategies like the strategy A and strategy B. So still with the Fermi rule and others could be a more general extension with the previous one. So some details here I just share you. Maybe if you have interest, you can read it from the paper. Like that, we put that structure evolution could be described by such a Markovian chain with transition matrix, and also the stationary distribution of the final chain could be like this. So finally, we can have arrive at the strategy A, whose frequency could be with this ODE function. The main result is that if we select the neutral selection, that means the beta is 0. So the population always reach consensus, but all the consensus states are stable, none are evolutionarily stable. However, if the selection presents, that means the beta does not be 0. Here, the population presents a small number of stable consensus states, and they are evolutionarily stable. So that's the difference. In more detail, you can see that if we put the neutral selection, so there's no selection here, we can see that all the consensus states are still stable, but not evolutionarily stable. We finally achieve the same, but not evolutionarily stable. However, in the case of the weak selection, that means we require the beta to be much smaller than 1. However, we can put such a general payoff matrix to formalize the new one. And we can divide it into 3 groups of the game model. For example, the first one is dominant type game. That means finally the consensus reach a homogeneous one, and only or A or B like that. So you can put in this corner or this corner. So only a dominant one. The second one is the coexist time. That means if such condition achieved, but finally the consensus states will be a kind of A and B coexisting in the same system. So that means there is such a chapter here, and all the consensuses finally reach over there. The third one is the bistable type. That means as the comparison of the dominant one, just this corner and this corner, they does not coexist, but at this time, this corner and that corner exist at the same time. So in this case, only this condition achieves that the final states could be a kind of homogeneous consensus, but they are bistable. The third case is non-weak selection. Here we can only use a kind of the simulation because the analytical result is not so easy. And we can see that homogeneous consensus are robust in the selection intensity. As this kind of that summary, we can show you that selection is kind of a double-edged sword. So generally, it may drive the two populations. As kind of we can extend it to multiple populations. So two populations here to a kind of non-consensus states when such selection is absent. However, when selection exists, so we can establish such a kind of a consensus, and the consensus is evolutionary stable. So that's the two edge. And as the time, I can show you another branch of the evolution gaming story, as we can find a new results on to achieve more optimization. For example, how is the probability that the players cooperate and decide a kind of a solution? The solution is to an empty hull or empty complete problems. However, such a solution is achieved by themselves. So the question is that we can show you that if in some cases, for example, in such a kind of a story, there is a lion who has been out of the cage, so we can put many guards to find that lion. So every corner here, every cross here, we should type to the guards and to watch the paths. However, we should think the least guards, because the number of guards here means the cost and the other expense. So we think we should put the least guards, and the guards can monitor every path of the graph or connectivity pattern. So here, as a more example here, you can put this if we regard the red one as a covered one, and the blue one is the uncovered one. So if we also map the covered states as a comparator and the uncovered one as a effector, here we can see that this is a vertex covered state with the cooperation or comparator and effector. However, the red one is not, the number is not the least. The least one is here. This is a minimum cover states with the cooperators. So the cooperators is the least. When we show you that we can use a kind of evolution game to achieve such a distributed optimization, and we should formalize the vertex cover problem as here. There is a simple graph, the vertex and edge. And the vertex cover stage is that means a small part of the vertices. However, there is some kind of for every edge in the graph, at least one vertex is in the cover state, at least one. So every edge should have at least one node in the cover state. So the minimum vertex cover state could be such a set as the least number. And we use the game model with the snow drift game. I think everybody here is very familiar with this model, because the two drivers to shuffle the snow drift, and we use such a very familiar pillar matrix. GISP is such kind of order, and we can see the time to show you the Nash equilibrium. Anyway, if the inequality curve stage, the Nash equilibrium here is a kind of straight one, right? So we get the first result is that for any given simple undirected graph, we find that such a vertex cover state is a strict Nash equilibrium. That means you can see that the minimal vertex cover state is a part of the strict Nash equilibrium. And the SNE is also a part of the VC, vertex cover states. So that means we can show you that if we want to achieve such MVC set, we should first focus on the SNE, then from the SNE to finally arrive at the MVC, right? And we also find if we want to achieve such MVC states, we should not only with the previous condition, not only with this condition, but also we should require that the memory-based fast response updating rule. Besides, there is some kind of the R times the maximum degree should be less than 1, and the memory length is larger than 2. At least two memory steps. So if these conditions could be satisfied, we can finally achieve such MVC states with sufficient running time. I can show you that the memory states effect because if for this case there is a non-minimum cover state. For example, this one is a cover state where the 4 nodes should be covered. However, if we have the memory true states only have 2, so still keep B, B, C, C, C like this. So still stay actually such a bad non-minimum cover states. However, if we can increase the memory length from 2 to 4, that means we can use every node here has such a long of memory. They finally could change from such a very non-minimum states, general step like this. Finally, we can achieve the minimum cover states. That means the 5 nodes here only need to cover the central nodes, and this is a minimum cover states. Only 1 node should be covered. This is the memory's length. Besides, such a memory could be a very robust. For example, if this is a minimum cover state here, and the central node is covered, however, if there is a kind of the perturbation, because for example, here this node is from uncovered state to covered. So we just updating the memory length, finally they should return to the minimum cover state. For example, here these 2 nodes are to be covered, but we still need 1 covered nodes. So they will return to the minimum cover state with only 1 step updating memory. So that's the benefit from the memory length, and such a kind of best response updating rule can help to maximize the memory's effect. However, we should also comment that because the memory length still we need more time to convert to the minimum vertex cover states like that. So that means the M1, if a larger or longer memory length, then we can more easier to arrive at the MVC state. However, at the same time, we need more time to arrive at the optimal solution. Other questions could be step further like this. We can still use the cooperation with the evolution game to find the new decisions or optimizations with all players, but they arrive at the decisions by themselves, not from the top, but from the bottom. And here we can extend our work from the static structure and the dynamic structure to switching structure, and also the time involving payoff with uncertainty and temporal contents, and even the spatial cover. For example, we can use such a evolution game to achieve a kind of the best strategy among self-interest users in the problem of the packet forwarding in wireless sensor network. So for example, 2 users are very decide whether or not to help forward the packet for another one. So this is a peer-to-peer. They may decide to forward and also decide to drop the packet. However, we should design such a kind of the cooperation mechanism to achieve the final information and package throughput performance be optimal. However, on the other hand, we assume that each user make the decision by themselves. So this work has been finished, and we still will be submitted very soon. So thank you.